All right, so we left off yesterday. I don't want to spend a lot of time on this, but we kind of got shorted just a little bit. We were looking at the derivatives as rates, and this was an example I wanted you to take a look at and think about. If you're blowing up a balloon, why does it initially seem like you're making a lot of progress, and after a while you don't? So if we look at these graphs, there's a bunch of graphs here. What are they? So the orange graph is a graph of y equals volume as a function of radius. Okay. Is that right? No, it's not the orange graph. It's the red graph. It's the red graph. Oops. Let me do. There we go. It's the red graph. The blue graph is a graph of y equals r as a function of v. Radius is a function of volume. Okay, so that means volume would be on the x-axis and radius would be on the y-axis. Okay, look at the derivatives. The orange graph is the derivative of volume with respect to radius, and the blue graph is the one that's going to be, the purple graph is the one that's maybe going to be the most useful. That's a graph of r prime of v, so the derivative of radius with respect to volume. If you want to explain why you have that experience of initially you make a lot of progress and very soon you start to have not so much progress, the purple graph is the one that does the best job of that, right? R prime of v is describing how fast the radius is increasing for an increase in volume, right? Initially, it's a really high number, right? A relatively small or just a constant rate of increase in volume is going to give me a really high increase in radius, right? Because that derivative has such a high value for low values of v. When the volume is low, changes in volume make the radius increase very rapidly. When the volume is large, and look at this purple graph. On the purple graph, this is the v-axis, and this is the r-axis, right? Actually, it's the r prime axis, right? But this is the v-axis, okay? When volume is large, r prime is really small, right? The rate of change of the radius becomes very, very tiny, and that's why you blow a breath into the balloon when it's big and you hardly see anything change. Okay, give me 1 to 5. Does that make sense? Okay, that's a good. It's just a good way to think about rates. Okay, how would we calculate r prime of v? For now, what we would have to do, we'll have another trick soon when we learn implicit differentiation, which is a new technique we'll learn. I can't remember exactly when that pops up. It's a little ways in the future. We'll have a better way of doing this. But for now, what we would have to do is we would have to take our original equation, our volume equation, and solve for r, isolate the r in terms of v, and I would just get this, right? I would get r equals the cube root of the quantity 3v over 4 pi. And I would just have to differentiate that, okay, to get that derivative. But in the future, we'll have a better way of doing it. Okay, any questions on that? Just kind of a cool application of this stuff. That's one of the real joys of studying like math and physics is I know this sounds incredibly geeky, but this is like one of the most rewarding things throughout my life. I've really enjoyed this. Just being able to kind of look at stuff and just think about, okay, why is that happening? What's causing that? What's a relationship there? Is there some kind of a realistic, logical connection there that you can see and understand? And that's really rewarding, I think. Okay, so some derivative rules. Here, you get a lot of bang for your buck on this page right here. We're going to add, we've only got one derivative rule right now, and that is, well, I guess we've got two. We know maybe even three. We already know the derivative of a constant is 0. We know the derivative, we'll add one more here. We know that the derivative with respect to x of x is 1. We added the generalized power rule the other day. And now we got a bunch of other ones that we kind of talked about this one a little bit. The derivative of a sum or a difference, we can just split into separate derivatives and differentiate term by term. That's really what this one is saying. That's what that one says. We know this one, but everything below this for sure is all stuff that we haven't even talked about. These are just new derivatives. So the derivative with respect to x of sine x is defined as cosine x. The derivative, that's wrong. The derivative of cosine x is not sine x, actually. That's not true. It's negative sine x. Got to fix that. And the derivative of e to the x is e to the x. Okay, that's bizarre and really cool if you think about that. If we look at an exponential function, let's look at this one for just a second. Let's do it on Desmos. I mean, this is just so crazy. Oh, a few years ago, when my own kids told me that I look exactly like Shrek, I decided I would just. I just own it. I'm not gonna worry too much about it. So there's y equals e to the x, right? Okay. Now, what's crazy about this is if I look at the slopes of tangent lines, and that's all that a derivative function does. Look what I get if I graph g of x is equal to the derivative of f of x. So f prime of x. It's the same function. Isn't that weird? That the value of the slope of a tangent line of e to the x is always exactly equal to the value of the function at that place? That's crazy, right? That they're the same thing. Look at that. Insane. How about what if we look at, let's look at, we'll call it h of x. H of x equals sine x. So there's a sine function. You guys are well familiar with the sine function. So let's call this, I don't know, j of x. J of x equals h prime of x. Oh, look at that. What's that look like? Just looks like a cosine function, right? And that sort of makes a little bit of intuitive sense, doesn't it? You can see that the rate of change of a sine function is going to be biggest at where the cosine function just happens to be at a maximum, right? The tangents have the steepest slopes for a sine function where a cosine function has its maximum. Yep. Yes, you do. So let's see. I think you can do that in here. So let's call this k of x, and it's going to be. Let's see if I can do h double prime. Maybe I have to just do prime prime. Yeah, look at that. And so it's negative sine x, isn't it? The black curve. If I take the green one and I multiply by -1, I'm just reflecting it over the x-axis. Everybody see that? Okay. Yeah. So if I do it again, so what's the derivative of negative sine x is going to be negative cosine x, right? So let's see if we can do it again. I bet it may not let me do this forever. So m of x equals, I bet it won't let me do this. Prime prime, oops, equals h prime 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 of x. Oh, I did it. How about that? Yeah. Yeah. What's that? Yeah. Hmm. Yep. And so if I did that again, right, exactly. If I did that again, it would be back to sine x. Yep. Yep.
Can you like see what E is? It's just a constant.
E is a constant. Yeah. Yeah.
It's the only number it does that.
Does what work? No, it doesn't. Look. Okay, these are good questions. Fun with Desmos. So if we we'll try a different one. So we'll call this n of x. If n of x is equal to, let's just make it like 10 to the x. Okay. Then, which is a little different than e to the x, right? There's e to the x. Okay. If I do p, we could only do 25 examples here because we can't use x. So p of x, if that's n prime, it's a little different. Only works with e. E is a special number like pi. It's called the natural number. We'll learn a lot more about e when we get into, I will give you guys some really solid insight into why e is so unique. But it depends on integral calculus to really understand that relationship, which we don't know yet. That's a little ways down the road. History of math? Yeah, it would be interesting for sure. That's what YouTube. Boy, there's all kinds of great like. You guys ever look at like Vsauce and stuff like that? I mean, yeah, there's some good stuff out there where you can just creation of an imaginary number. Yeah, where that came from. Poorly named because it's not that imaginary. Okay, so let's try a little bit. All right, we have these derivative rules now. If I want to differentiate these functions, let's take a, for example. So what's f prime of x? If f of x is 3e to the x, what's f prime of x? 3e to the x, right? Because the 3 stays out front, the derivative of e to the x is e to the x. So there it is, right? Okay, how about this one? F of x is x squared plus e to the x. What do we get? 2x plus e to the x. There you go. F of x is sine x minus e to the x. F prime of x is equal to what? Do you remember? Cosine x minus e to the x. Okay? No big deal. So now we got all this stuff we can do now that we couldn't do before. Okay, what about something like that top one? How could I differentiate that top function? Okay, it looks complicated, right? Any ideas? Okay, I'd have to distribute, right? Because although we can say this is true, the limit of f of x times g of x equals limit f of x times limit g of x. That's true, but the derivative of, I don't want to say this. Use different notation. The derivative with respect to x of f of x times g of x is not equal to f prime of x times g prime of x. So I can't just differentiate the first factor and multiply that times the derivative of the second factor. That's not the way products work. So I would have to expand this out, which I could do, right? If I FOIL that out, what am I going to get? Let's see. The biggest term I'm going to get is going to be, you guys tell me, what's my, this is good mental math for you. What are we going to get here? Negative 8x cubed. What about my x squareds? What am I going to get? Okay, what else though when I distribute? Okay, so what's the sum? I'm going to get a 12x squared and a minus 10x squared. So a 2x squared. What about my x terms? I'm going to get a 15x. That's it, right? Plus 15x. That's the only x term. Okay. So if I write that out, if I expand it out, it becomes a polynomial. Now it's easy though, right? If it's a polynomial, we differentiate a polynomial term by term. So what's h prime going to be? What's next? 4x plus 15. Okay, good. So how about the derivative of this bottom one? We're stuck, aren't we? We don't know how to do that because that is a product and there's no way around it. I can't just expand that out and make it a polynomial or something. So this one we can't do. Yet, okay? We need to derive a product rule, don't we? Okay, this is kind of a weird derivative. So I'm going to walk, or weird proof. I'm going to walk you through this one. Does this step make sense? If we're going to define P of X as the product of F of X times G of X, okay? Then what is P prime of X? Well, we're just going to use our definition of, now why did I call that F? Okay, I guess I'm going to change this. I guess I'm going to change that to an F. I mixed I got a few little mistakes in here, don't I? So we'll just make those Fs. So F of X, oh, I can't make it F, can I? Oh, never mind. It was right. What am I saying? It was right. Yeah, there we go. So P prime of X then would be what? Okay, it's going to be P prime of X is by definition, you tell me, what's my limit definition, my most general definition of P prime of X? Limit of what? Well, what's our, like, it's the limit of the quotient or the difference quotient, right? What's the difference quotient for P? P of X plus H minus P of X over H as H goes to 0, right? Okay, so then let's color code this. What is P of X plus H? If P of X is F of X times G of X, what's P of X plus H? Isn't it that? Right? F of X plus H times G of X plus H, right? Minus P of X, whoops, wrong color. P of X, well, P of X is just that, right? Okay, so does everybody buy that that's what the difference quotient gives us for P of X? Okay, so now what? What are we going to do? So this is one of those really rare situations where we're going to do some algebra where we add 0 instead of multiply by 1. About 99 times out of 100, we're going to multiply by 1. And rarely do we do this, but this is kind of a cool deal. So what do we get here? First step. Notice that the first term on the top and the second term on the top, just they don't change. But I'm going to add 0 in the form of plus f of x plus h times g of x minus f of x plus h times g of x. So I've just got a positive term and the exact same, the negative of that term, the opposite of that term that I'm adding together, which add to 0, right? How come? Can you tell me, why might I have done that? Okay, well, but if I cancel it, I'm just undoing the step that I just did. So there must be something more to it than that. Remember, I can break this into individual limits too, right? Would there be a reason for maybe grouping, these two terms together and those two terms together? Any ideas? So what if we color code those just a little bit? So I'm going to group the first two terms together in green and the second two terms together in purple. Is there a way to reconfigure the green and the purple? Probably by factoring, right? What else could we do? Could I factor something out of both of those that might be helpful? What could I factor out of the green? Oh, okay, I could factor out an f of x plus h. That's a common factor, isn't it? From the green. How about from the purple? G of x. Okay, so let's see what that does. Okay, so I'm going to split, and I'm also going to do this. I'm going to split this into two separate fractions, right? Instead of one big fraction with a common denominator, let's split it into two separate fractions. And this first fraction, I'm going to factor out an f of x plus h. In the second fraction, I'm going to factor a g of x out front. Okay? Well, how come? What does this look like right here? What is this thing, the limit of that compared to the limit of that? How about the green box? The limit of that green box as h goes to 0 is defined as what? What is it again? Yeah, that's g prime of x, isn't it? Right? That is the limit of the difference quotient for g as h goes to 0, isn't it? How about the blue? Yeah, that's f prime of x, isn't it? Right? So look what we get. Oops. We end up with, oh, what happened there? I don't know. It's supposed to be f of, I don't know what happened there. F of x plus h times the limit, and I split it into limits. Oh, I know what it is. There's something, yeah. Yeah, that one. I just got to get rid of that guy. I don't know why that guy got stuck there. Right? So I've got the limit. I can split up the limit of a product into separate limits, right? So I can take the limit of this piece by itself times the limit of this piece by itself plus the limit of g of x by itself times the limit of that whole piece by itself. And you guys already saw that this is just g prime of x and this is just f prime of x. And so look what we did. That's really cool. We got the product rule out of this then, right? We end up with f of x times g prime of x plus g of x times f prime of x. That is the product rule. Okay? So here it's summarized. The derivative with respect to x of f of x times g of x is just that. F of x times g prime of x plus g of x times f prime of x. Now, because addition is commutative, it doesn't matter, and associative, it doesn't matter, which of these two I do first, right? Which term I do first makes no difference. A lot of times we say it this way: if we let u equal f of x and v equal g of x, then the derivative of u times v, because it gets kind of cumbersome to have all these, like, doesn't that look just kind of like too much visually to see f of x is in there and f prime of x? It's a lot easier if we just think of the function f of x as being u and the function g of x as being v. Then the derivative of the product of u times v is just u v prime plus v u prime. A much more compact and simple way of seeing the rule, right? And we could extend the product rule if we had a derivative of a product of three factors. Well, look what it is. It's just going to be the derivative of u times v times w is u v w prime plus u v prime w plus u prime v w. And you could extend that, right, to as many factors as you wanted to. Okay, make sense? Let's try it. It's a really easy rule to apply. So now we can go back and do this derivative. So what's y prime going to equal here? Okay, what was it? We're going to have the derivative of u times v is u v prime, right? So what's that going to be? X times e to the x. I'm going to write derivatives in red, okay, so we can see the process here. Plus e to the x times 1, which I wouldn't even have to write, would I? Okay. And I end up with y prime equals x e to the x plus e to the x. Okay, give me thumbs on that. How we doing?
Explain how you got to y prime equals x.
Okay, because I'm using the rule, right? I'm using the rule. The derivative of a product is first times the derivative of the second plus second times derivative of the first. Okay, right? So what did we do here? I did first times derivative of the second plus second times derivative of the first, right? You see how that works? Okay. Let's try another one. Let's, before we jump to quotient rule, let's just try, I'm going to make one up here. Let's try, how about this? You guys try this real quick on your own. Let's do f of x equals 3x squared sine x. Okay, calculate f prime of x. What'd you get? We'll go through the process, but let's just write an answer to that. But what'd you get? Who feels confident about their answer? Nobody. Okay, what'd you get?
I got 3x squared cosine x plus sine x 6x.
Okay, I'm going to put the 6x sine x. So when we simplify stuff, this is just kind of a little math convention. We always like to put constants first, then we put powers, and then after that we put functions like cosine or sine. How come? It makes a little bit of sense to me because if I put the sine x first, then we like in front of the, then do we think, for example, that the other stuff is inside the sine? You know, there's just a little bit of ambiguity there. There shouldn't be, but there is, right? So we'd have to enclose everything in the, if there's more than just an x, we'd put it in parentheses, but you know, people don't always do that. And so that's why we always kind of put the trig functions at the end. Okay, now how do we get that? How do we get that? Well, we do first. So here's another question that might come up. What do you do with the 3? You have options, and there's no right or wrong answer. What are my options with that 3? I could pull it out front and then leave it there, right? And just do the derivative of the product of x squared times sine x and then redistribute the 3. That's fine. I don't do it that way. I prefer to just do this. Like, it's so easy to have 3 times x squared. What's the difference between 3 times x squared and x squared? So I would always group it like that. Make that put the constant with the power, okay? So that'll be our first part. That's our second part. Let's go through the product rule then. So we get first times derivative of the second, right? Plus second times derivative of the first. Good? And then we would just rewrite it like that. Okay? Give me 1 to 5. Does that make sense? Okay? 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 And you get tons of practice on this. Actually, I didn't assign that many problems because once you've done a couple product rule problems, it's, you know, I mean, they're all the same. Okay, quotient rule. I'm not going to go through the proof for quotient rule. This is it. Okay, it looks like a mess, but it's easier to see it this way. So the derivative of a quotient of f of x over g of x is equal to g of x times f prime of x minus f of x times g prime of x all over g of x squared. Okay, so this one, order is important because on the top we have a difference, and real numbers are not associative, or variables or anything are not associative or commutative over the operation of subtraction, right? 7 minus 3 is different than 3 minus 7. So this time we have to keep the order the same. We can't change it or we'll get a wrong answer. Now it's much easier to look at the quotient rule with u's and v's. The derivative of the quotient of u over v, where u is some function of x and v is some function of x, is v du minus u dv. And when I say d, I'm kind of taking a shortcut. What we really mean is v du dx minus u dv dx, right? Because technically u prime is the derivative of u with respect to x here, isn't it? Right? So really, I'm differentiating with respect to x. But we take shortcuts. And when it's easier to remember this if you just think of v du, v times the derivative of u, minus u dv, meaning v prime, u times the derivative of v over v squared. The way I always remembered that when I first learned calculus is it sounds like video, VDU, sounds like video. That's kind of dumb, but everyone has their own little mnemonic devices. That's how I remembered it. Since I've heard better versions, this is kind of what people use a lot of times. The saying low D high minus high D low is what you have on top. U is the high function, V is the low function in this quotient. So you have low D high minus high D low. Okay, that's the way a lot of people remember it. Divided by V squared. Okay, low D high minus high D low. Whichever one works best for you. I like video, but whatever. So here we have y. Let's calculate y prime. Okay, so what are we going to? Low is x squared plus 1. High is 5x minus 2. So what am I going to get from my quotient rule then? What's this going to give me? Abby, what do you think? What am I going to get here?
Well, you're going to have the 5x minus 2, so that's the
Right.
I mean, no, so you had the low first, right?
Yeah, there you
So
go.
x squared plus 1, and then you have
So, and I need that in parentheses, right? Because it's a quantity. Okay, so I've got the quantity x squared plus 1 times
and then just 5.
5, because the derivative of the top. So low d high, the derivative of the top is just 5 minus,
And then a 2x, is right?
okay, right, but I'm just going to follow, I'm going to follow the high d low,
Oh, yeah.
right? Low d high minus high d low. So what's high then?
High would be just 5 again, right?
5, no,
Oh,
5x minus 2.
Well, how do we get the derivative of 5x minus 2 is 5? I mean, I think it is, but how?
How do we get that? Okay, the derivative of 5x minus 2 is the derivative of 5x minus the derivative of 2. What's the derivative of 5x? Derivative of 2 is 0, right? Okay.
and then 2x.
There we go. Okay, so again, we've got low bottom, right? D high times derivative of the top minus high top function. D low, the derivative of the denominator is what? 2x divided by the bottom squared, right? So that's the calculus. Now we just have to go in and do a little cleanup is all, right? We'll just expand the top out, collect like terms, and what do we get? Y prime equals 5x squared plus 5. I'm going to distribute a negative 2x to this stuff, right? I have to distribute the negative sign and the 2x. So I'm going to get a minus 10x squared plus 4x all over x squared plus 1 squared. So if I collect like terms, I get a negative 5x squared plus 4x plus 5 over the quantity x squared plus 1 squared. So do I need to expand out the bottom? No, I don't. And you might wonder why. Okay, that'll be abundantly clear in the future. When we take derivatives, if anything, we want to have them as factored as possible because a lot of the things we do with derivatives depend on them being factored. Okay, so we don't ever want to unnecessarily expand something out. We had to expand the top out because I've got this minus sign in the middle. And so it's not in factored form to begin with, right? Everybody see that? Okay. All right, questions on that one? Give me 1 to 5 on that one. Does that make sense, those steps? And you just kind of just following that pattern over and over again. Before you know it, it just becomes second nature. Okay, how about this one? Walk me through this one. Yes, sir.
On the previous one,
Mhm.
what was the answer? Like, is that
Right
just
there.
the answer?
That's it right there.
Just turn that in.
Mm-hmm. What else are you going to do? Mm-hmm. Yeah. How about this one? Okay, Liliana, talk me through this one. Low D high minus high D low. So where do I start with this one? First step. What's low? X squared plus 1. Okay, so there's, whoops. There's low, x squared plus 1. What's D high? Is derivative of 2 e to the x. What was the derivative of e to the x again? E to the x. Okay, so derivative of the top then would just be 2 e to the x, right? Okay, so there's low D high minus, and that's got to be a minus, it's not a plus, high. So what's high? 2 e to the x. Okay, so I guess I don't need that in parentheses. Well, I'll do it. E to the x times d low. 2, well, what's the derivative of x squared? I think you said it. I just didn't hear it. 2x. There you go. Yep. 2x. Okay. Divided by what goes on the bottom? Okay, good. Whatever the denominator, whatever it is, squared. So in this case, we've got x squared plus 1 squared. Okay, so we got to go into cleanup mode. Now, on the top, I could expand this whole thing out. I could, it's fine. But I really want it to be factored anyway, right? So let's take a different approach. Is there anything I could factor out of the top? 2e to the x, yeah. So on the top, I could take out a 2e to the x, leaving me with all this stuff, right? Everything in those glasses shaped, right? A little bubble there. So if I've, oops, wrong thing. Wrong thing. It's the wrong bubble. This bubble. No, not that bubble either. Holy smokes. That bubble is what's left behind, right? If I factor out the 2e to the x. So what's that going to give me? X squared plus 1 minus 2x, right? So just minus 2x plus 1. Agreed? Okay. All over, whoops. All over x squared plus 1 squared. Okay. That would be a good answer. And I could even on the top, like you won't see a need to do this right now. And on the assignments, it won't expect you to do this. But if I were going to factor that even further, could I write the top in an even more factored way? Yeah, I could if I really wanted to. I could write this. This is just the quantity x minus 1 squared, isn't it? Right? So 2e to the x times x minus 1 squared over x squared plus 1 squared. Soon you'll see why we want to do that when we start doing stuff with these derivatives we're practicing now. Okay, but this would be fine. That would be fine. If you just distributed the 2e to the x on the top on the assignment, it would mark that right. It's not expecting you to factor these at this point. Okay. All right. Good work. So though I'll put up both of those. They're both relatively short assignments. You want a work day tomorrow or Friday? You take your pick. Friday? That better?